The pace of cyber evolution these days. It's just incredible. We're not talking about simple static networks anymore. We're dealing with these massive, complex, really dynamic environments. Think huge cloud setups, countless devices connecting, and, well, sophisticated attackers, even nation states, who are now using things like machine learning. And this huge shift, it demands a totally different way of thinking about defense. The old ways of doing penetration testing, the sort of manual checklist approach, they're really hitting a wall. The scale and complexity are just too much.
That's exactly right. And today, that's what we're diving into. The motivation behind this, well, necessary shift. We're looking at the source material, specifically the arguments for using reinforcement learning, or RL, to automate and really modernize penetration testing. The big question we're tackling is, why do we have to move to this model-driven approach, and what are these models actually trying to do?
Right. So our mission today is to walk you through why the current methods are struggling, what RL brings to the table, and the basic idea behind automating a whole attack campaign. This is really your guide to understanding the why behind the next generation of cyber defense.
Okay, so just to make sure we're all on the same page, let's quickly touch on RL again. Remember, an RL agent, it operates in some environment, right? Over time steps. It chooses an action, sees what happens in the new state, and gets some kind of feedback, a reward. And the goal is for the agent to learn a strategy, a policy that gets it the most reward over the long run. Technically, we talk about minimizing the discounted sum of expected future rewards.
Okay, discounted sum of expected future rewards. Let's maybe make that a bit more concrete for everyone listening.
Yeah, fair enough. Think of it like a strategic investment. The reward is like money, and the discount factor. That represents risk, or maybe just impatience, Does the agent take a small, pretty certain reward right now, like a quiet action, low risk of getting caught? Or does it go for a potentially much bigger payout later, even if the action is riskier, noisier, maybe costs more resources, like going for full control of a key server? The agent learns to balance that risk versus reward over the whole campaign. It learns through, well, doing it, how to be effective and sneaky. That whole interaction learn by doing model, that's the heart of model-driven PT.
Okay, so before we get all excited about these smart agents, we really need to grasp why the old ways aren't cutting it. The material makes it super clear. Existing methods really stumble over technical hurdles, mainly when it comes to generating attack graphs.
Right, attack graphs are sort of the classic way to visualize security. They're meant to be these comprehensive maps, mathematical models showing vulnerabilities, what you need to exploit them, the preconditions, and what happens after the postconditions. All across the network. They sound great, but the problem is when you try to actually build one for a big network, thousands of machines, you hit this wall. It's called exponential growth.
Exponential growth.
Yeah.
We hear that term, but can you break down what that actually means in practice? Why is it such a showstopper?
Absolutely. So the traditional ways, they map out the network state based on the number of hosts. Let's call it N. Since each host can be in different states, compromised, reachable, whatever the total number of possible network states can grow incredibly fast, the rate is like 50N. And just to give you a feel for that, if N is just 50 hosts, which is tiny, really, for a company to do 250 as well. It's over a quadrillion states. Trying to compute and analyze a graph that size, it's just impossible. It would take like millennia.
Wow. Okay, so the materials analogy is spot on. Then traditional models spend more time trying to read this impossibly huge map than actually figuring out a route. They just create these massive haystacks.
That's a perfect way to put it. Yeah. And this computational nightmare basically forced researchers to make some pretty drastic compromises. They had to figure out ways to get the complexity down from, impossible exponential growth to something polynomial, something computers could actually handle.
Right. So how do they do that? What was the trick to get that efficiency boost?
Well, they had to simplify a lot. Instead of modeling the state of every single host and how they all interact, they started focusing just on the vulnerabilities themselves, or maybe the vulnerabilities on specific hosts.
Can you give us some examples of those approaches, the ones that made things polynomial?
Sure. There are methods like TVA, which stands for Exploit Dependency Graphs, and tools like Mulval, which uses logic programming. These manage to cut the complexity down significantly to things like math call N3 or math call N2, which is, a huge leap. It makes the problem solvable, at least in theory. But, and this is a big but, they achieve this speed by essentially throwing away a lot of the network context. They don't embed the full network model.
And what assumptions do they have to make to get that speed? Are there limitations baked in?
Oh, absolutely. One of the really big simplifying assumptions they often rely on is called the monotonicity assumption. Monotonicity basically means that once an attacker gains some privilege or access, they never lose it. Access only goes up.
Wait a second. That sounds completely unrealistic, right?
Right.
In the real world, access gets revoked all the time.
It totally is unrealistic. Yeah, think about it. Real attackers deal with session timeouts, automated defenses kicking in, patching cycles, maybe even a sysadmin noticing something weird and kicking them off. You know, a security system might detect activity and just isolate the machine. Boom, access gone. By assuming monotonicity, these simplified graphs ignore all that. They paint a picture that doesn't really reflect how security actually works, all for the sake of making the math easier.
You also mentioned NetPA being even faster, MACAL-N, which sounds really efficient. What's different about that one?
Yeah, NetPA is quite efficient, and sometimes it actually does keep the idea of individual hosts in its model, which is good. But the graphs it produces are cyclical, meaning the paths can loop back on themselves. Tools like Mulval usually create acyclical graphs. They only go forward, no loops, which makes analyzing the path simpler. You know where you're headed. So it's always these trade-offs between efficiency, detail, and realism. But almost all these methods share one fundamental critical weakness.
Which is the known vulnerability bias. That sounds like a major problem.
It really is probably the most significant flaw because it hits right at the core issue, realism. These automated tools, they almost exclusively rely on structured data from vulnerability databases like CVSS scores, right? The Common Vulnerability Scoring System. So the picture of the network they build, the attack paths they find are heavily, heavily biased towards only these documented known weaknesses.
Okay, let's paint a picture. Say an attacker finds a clever way to combine like three things. Maybe a minor configuration error with a low CVSS score, an old web server version, and just a simple network setup mistake. Individually, none are critical. What does the traditional model see?
Well, the traditional model, looking mainly at CVSS scores, might barely register those things. It might see 3 low-priority issues and just ignore the combination, or assign it a really low risk. It's looking for that single high-scoring vulnerability, the smoking gun. But a human attacker, a good red teamer, they see the context. They see how those minor things interact, the cyber terrain, as the material calls it. They exploit that synergy. The traditional model completely misses that realistic contextual path. It fails to give you the strategic insight you actually need.
So the bottom line is, trying to map everything top-down is computationally impossible and gives you a skewed view anyway. The goal of this new research has to be different, using learning, interaction, to build models that are scalable, grounded in reality, and prioritize the kinds of strategic paths a real attacker would actually look for.
Exactly. Stop trying to map the entire universe in infinite detail. Instead, teach an agent how to navigate that universe smartly. Focus on finding the optimal paths, the efficient ones, not just listing every single theoretical possibility.
And that shift from mapping to navigating, that's where reinforcement learning comes in, right? Because RL is inherently about that kind of interaction, that sensac learn loop that humans do.
Precisely. The agent learns by trying things out, getting feedback, and getting smarter over time. In the early research using RL for cyber stuff, it was often focused on pretty simple tasks, basic pathing, finding a route. A lot of the initial work just applied standard algorithms like deep Q-learning, DQN, to solve simple get from point A to point B network problems. The goal was often just to show, proof of concept, that an agent could learn to escalate privileges, even if the exact best way wasn't known beforehand.
But real cyber attacks aren't just point A to point B, they're campaigns, right? The environment is huge, the number of possible actions is enormous. How did researchers start adapting these basic RL algorithms for that kind of complexity?
Yeah, they hit that wall pretty quickly. You couldn't just throw standard DQN at a big corporate network and expect it to work. The state space, the action space, just too big. Way too complex. So that really pushed the development of domain-specific adaptations. We started seeing specialized deep RL models emerge, things like the double agent architecture or DAA and NDSPI DQN. These were designed specifically to handle the randomness and just the sheer size of the cyber environment.
The complexity management piece is key. I saw mention of hierarchical action decomposition. That sounds like a really clever way to handle it, almost like how people break down big tasks.
It's absolutely crucial for making this scalable. Yeah. Hierarchical action decomposition lets the agent think on 2 levels, basically. There's a high-level decision, like, okay, my goal now is to compromise the finance department's network. And then there are the low-level actions needed to actually achieve that goal right now, which specific exploit to use, which port to scan next.
That almost sounds like it's modeling how a red team works internally. You have the team lead setting the strategic goal, and then operators executing the specific tactics. It must drastically cut down the number of things the AI has to consider at any one time.
That's a perfect analogy, yes. It stops the agent from having to evaluate every single possible specific exploit every time it makes a move. It just needs to decide the kind of thing it needs to do next. And that efficiency gain was huge. It allowed the research to move beyond just finding any path to actually solving specific, operationally relevant objectives, things that real security teams care about.
Okay, so let's talk about those specific tailored tasks. It sounds like the focus shifted to defining success in terms of achieving real-world goals, not just, running some code.
Exactly. And this required getting really clever with what's called reward engineering, designing the feedback the agent gets,
Yeah.
and also modifying the underlying mathematical structure, the MDP, to really align the agent's learning with specific security outcomes.
Like finding the path to the most sensitive data.
Precisely. So you see objectives like crown jewel analysis, CJA. The goal here isn't just finding a way in. It's finding the best way, most efficient, maybe, but also the quietest, the stealthiest path to get to that really high-value target, the crown jewel in the network. It's about strategic impact.
And once you're in, getting the data out without setting off alarms.
Yep, that's another key task, finding optimal exfiltration paths. Here, the agent is specifically rewarded for discovering routes that minimize the chance of detection while moving stolen data out. This might mean learning to prefer certain types of network traffic, avoiding noisy actions, or maybe making lateral moves that look like normal user activity.
But how can RL model something like stealth? Isn't that kind of subjective? How do you give a reward for being quiet?
That's a great question, and it's fundamental. It really boils down to sophisticated noise cost modeling. Stealth isn't subjective to the AI, it's quantified. Actions that are known to be noisy, like aggressive scanning or using certain loud exploits, are given large negative rewards. They have a high cost associated with them. So the agent learns that to maximize its overall reward, it needs to minimize the sum of these negative costs. It naturally learns to prefer the path of least resistance, or rather least noise, even if that path takes longer or involves more steps. And finally, you also see tasks framed as capture the flag CTF exercises. This turns the complex pen test environment into something more like a game, with clear rules and objectives, making it easier to apply these RL techniques.
Okay, this level of detail in setting objectives brings us right to the core math, the Markov decision process, or MDP. This is where the rubber meets the road, translating the messy reality of a network attack into the formal language the RL agent understands. States, actions, rewards, probabilities. Let's break down how each of those maps, starting with the state.
Right, the state space. This is like the snapshot of the network at any given moment. And it has to be more than just which machines are connected. It typically includes which hosts the agent knows about, whether they're reachable, whether they've been scanned or discovered, and crucially, what level of access or privilege the agent currently has on each machine. It's potentially a huge multidimensional thing, and just representing it efficiently is a big part of the challenge.
Okay, then the actions. These are the moves the agent can make.
Correct. The actions are the basic operations the agent can perform, and they usually map pretty directly onto what a human penetration tester does. Things like scans, reconnaissance, finding out what's there, exploits, trying to gain that initial foothold or elevate privileges, and privilege escalations moving from, say, a regular user account to an admin or root account. The agent has to learn the best sequence of these.
Now, transition probabilities.
Right.
Networks aren't perfectly predictable, right? Things fail, defenses work sometimes. How do we capture that uncertainty?
Exactly. The transition probabilities represent the chance that a chosen action will actually succeed and move the network into the state the agent intended. And this is often where the model connects back to that vulnerability data we talked about. The probability of an exploit working might be directly derived from its CVSS exploitability score, for instance. If an exploit is known to be very reliable, it gets a high probability. This gives the agent a way to quantify the risk versus the potential reward of trying a particular action.
And finally, rewards.
Yeah.
You mentioned earlier this is maybe the trickiest part, the most inconsistent across different research, because it literally defines what motivates the agent.
It really does, and you have to engineer it carefully, otherwise the agent might learn weird or unhelpful strategies. We usually think of rewards in three main categories. First, there are negative costs. These are like penalties for doing things, maybe a small cost for every action taken, just to encourage the agent to be efficient. Or, importantly, much larger negative costs for doing noisy things like firing up a loud scanner that's likely to get detected. This pushes the agent towards stealth.
Okay, penalties. Then there's the big prize, right?
Right, the terminal reward. That's the big payout the agent gets only if it achieves the main objective, like getting admin rights on that critical crown jewel server. It's a sparse reward, often only given at the very end, defining mission success.
And the third type, the one you said, helps overcome that bias problem. Intermediate rewards based on cyber terrain. This really seems like the key innovation.
It absolutely is key for realism. Intermediate rewards are smaller bits of feedback given during the attack simulation based on the context, not just on finding a known vulnerability. They let the model understand environmental risk, going beyond just the technical severity score of a flaw.
Can you elaborate on cyber terrain? What does that actually mean in the model, and how does it turn into rewards?
Yeah, so cyber terrain, think of it like military intelligence mapping the battlefield intelligence preparation of the battlefield, IPB. It means modeling the network's defenses and structure, not just its weaknesses. So, for example, a firewall isn't just something that might block you, it's mathematically modeled as an obstacle.
How do you model a firewall as an obstacle in the math in the MDP?
Well, there are a few ways. A simple way is to assign a huge negative intermediate reward if the agent tries to communicate across that firewall boundary without having the necessary prior access or, say, credentials, like a big penalty. Or, maybe more realistically, you set the transition probability of succeeding in that communication to be extremely low, maybe near zero. The agent then learns that attempting that action is just futile, a waste of time and resources, unless conditions change.
Okay, that makes sense. What about something like an intrusion detection system, an IDS?
An IDS could be modeled as like a field of fire, a high-risk zone. If the agent performs an action within a network segment monitored by an IDS, maybe the state transition includes a high chance of triggering a detection event, which comes with a large negative reward. The agent then learns, okay, it's dangerous to operate here, and will try to find ways around that subnet, or maybe use only very low noise techniques if it absolutely has to go through it.
So this idea of modeling the terrain leads naturally to that layered approach to building the MDP that the research talks about.
Exactly. It's like building up the complexity step by step. You start with a generic MDP, just basic connectivity. Then you add the terrain elements, the firewalls, IDS, to get the terrain MDP. Next, you might layer in the specific capabilities or limitations of the attacker you're trying to simulate. Maybe they only use certain types of exploits. That gives you the adversary MDP. And finally, you tweak the reward function for the specific mission, maybe CJA, maybe exfiltration to get the task MDP. This layering lets you tailor the simulation very precisely.
So getting this sophisticated MDP modeling right is one major research challenge. What are the other two big hurdles that need to be overcome to make automated pen testing practical?
The other two are absolutely critical for dealing with real-world messiness and scale.
I'm guessing the first one is that the attacker rarely knows everything about the network.
You got it. The first is tackling partial observability. We have to move beyond assuming the agent has perfect knowledge, the standard MDP assumption. We need to use partially observable Markov decision processes, or POMDPs, because that's reality, right? An attacker, human or AI, works with incomplete information. Scans get outdated, things change, they have a fuzzy picture of the network.
That sounds exactly like the day-to-day reality for a human red team operator. You run a scan, but by the time you act on it, maybe something's changed. The PUMDP is trying to bake that uncertainty right into the AI's planning.
Precisely. The agent now has to learn not just the best action to take, but also sometimes the best information-gathering action to take to reduce its uncertainty. It's a much harder problem computationally, but essential for realism. And the third major thrust, it's the classic computer science problem, scalability. How do we make these complex learning algorithms actually work on massive enterprise-scale networks with tens of thousands of hosts? Just getting the algorithms to find a good strategy without running forever or using infinite memory is a huge challenge in itself.
Okay, so we have these three really tough interconnected challenges. Building realistic MDPs, handling partial observability with POMDPs, and making it all scale up. How do researchers make sure all these different efforts are actually pulling in the same direction? Is there an overall goal?
Yes, and that's where the concept of whole campaign emulation, or WCE, comes in. WCE is proposed as this sort of unifying long-term research objective. It's a framework meant to align all these different pieces of work. It helps ensure that progress in say making POMDPs more efficient, is seen as contributing to the bigger picture, automating an entire realistic penetration testing campaign from start to finish.
So the idea is to view the whole campaign not as one single, giant, impossible problem, but more like a series of steps or stages.
That's the core strategic decision, yeah. Break it down. The WCE framework sees the campaign as these modular stages. Let's call them G1, G2, G3, etc. Maybe G1 is initial recon, finding a way in. G2 is moving laterally inside the network. G3 is achieving the final objective, like grabbing data. And each stage involves a sequence of smaller steps, actions, epsilon.
But breaking it down like that, it seems like there's a bit of a debate in the research community about the best way forward, solve the whole thing at once versus focusing on the modules.
Yeah, there's definitely an ongoing academic discussion there. One viewpoint argues for the pure goal, eventually removing the boundaries between these stages. Work backwards towards creating a single, massive, unified MDP for the entire campaign. This ideal model would have only one final big reward at the very end when the overall mission succeeds. The idea is this forces the AI to learn a truly holistic end-to-end strategy.
Why is that unified approach so incredibly hard to actually achieve, though?
Yeah. Well, it slams right into a fundamental problem in RL called the credit assignment problem. Imagine the agent finally succeeds after taking, 10,000 actions over simulated weeks. How does the learning algorithm figure out which specific actions, maybe way back near the beginning, were the really crucial ones that led to that final success? When the reward is so delayed and sparse, it's incredibly difficult for the agent to learn effectively, especially in a state space as vast as a large network. The learning becomes really slow, really fragile.
Okay, so the alternative, the more pragmatic approach, is to stick with the stages. Focus on mastering those first.
Exactly. That's the dominant view, the more practical path. Keep the focus on developing really good, specialized RL solutions for each stage, G1, G2, etc., and then figure out how to link them together within the WCE framework. Solve reconnaissance well, then solve lateral movement well, and integrate them.
That sounds much more like how automation usually gets adopted in complex fields, doesn't it? You automate pieces, acting as a force multiplier for the humans, rather than trying to replace the whole process overnight.
Precisely. It aligns much better with how technology actually matures and gets deployed. Think technology readiness levels, TRLs. By focusing on modular stages, you can get solutions for the easier parts, like maybe initial network mapping to a high TRL much faster. They can provide real value sooner. You don't have to wait until you've completely solved the entire, incredibly hard problem of end-to-end automation, including perfect scaling and perfect handling of partial observability all at once. WCE provides the structure to plug in those advanced pieces as they become ready.
Yeah, that makes a lot of sense. It's a compelling case for building up the intelligence piece by piece, making it useful along the way, rather than waiting for some perfect, maybe unattainable AI.
And it provides that necessary common goalpost, ensuring that all the different research efforts, even the very specialized ones, are ultimately judged by how well they contribute to that end-to-end strategic emulation. #ChagTag outro.
Well, this deep dive has really laid out the case, hasn't it? The fundamental reasons why we need to modernize penetration testing. Those traditional top-down attack graphs, they just can't keep up with the scale, and worse, they suffer from that built-in bias towards only known vulnerabilities, the CVSS scores. They're drawing maps that just don't match the real world anymore.
That really is the core takeaway. And the proposed solution, the path forward, is reinforcement learning, but RL that's been carefully, meticulously engineered for the unique challenges of the cyber domain. So for you listening, the key things to remember are, first, achieving realism isn't about just counting vulnerabilities. It's about layering in context that cyber terrain. Modeling defenses, modeling risk. We engineer rewards to reflect actual operational risk. Firewalls become obstacles in the math. IDS become danger zones. Stealth becomes minimizing costs.
And all these separate research threads tackling the fuzziness of partial observability with POMDPs, fighting the scaling battle, they're all being guided by this overarching goal of whole campaign emulation, WCE. It's this modular stage strategy that seems like the most practical way to eventually automate the complex strategic decision-making of an entire cyber attack campaign. It's really interesting how the purely technical challenges in ML are starting to mirror the strategic thinking of a human attacker.
It really is. It's becoming a kind of mathematical representation of strategic thinking. But, even as these models get incredibly sophisticated at optimizing paths based on known vulnerabilities, terrain, and quantified risk, they're still working within the parameters we give them, defined technical boundaries.
Which brings us to that final thought to leave everyone with.
Right. If WCE aims to automate the entire cyber campaign by mastering this sequential strategic decision-making, what's the next frontier? What's the non-technical human element of how real adversaries behave? Things like maybe an adversary's personal tolerance for risk, or their creativity, their intentions. What human factor does an AI need to model next to achieve truly complete whole campaign emulation? And maybe more importantly, how would you even begin to quantify something like that?